Have you ever just stopped and thought about what's holding our world together? I mean, quite literally. From the skyscrapers we work in to the cars we drive, there's this invisible art form happening all around us. It's a process that permanently fuses metal into the very structure of our lives. So today, let's dive into this hidden world of welding. So, let's start with the basics. What exactly is welding, and why is it so incredibly important? It's so much more than just melting metal. It's the absolute bedrock of modern manufacturing and construction. Okay, so the official definition sounds a little technical, I know, but the core idea is actually super simple. Welding is all about joining materials, usually metals, by heating them up so much that they melt and literally fuse together. When they cool down, they're not two pieces anymore, they're one single continuous piece. We're talking about a bond at the molecular level. And its use is just staggering. I mean, think about it for a second. The planes in the sky, those massive cargo ships crossing the ocean, the bridges that span our rivers, and the very frame of your car. It's absolutely essential for the buildings we live and work in, and even the power plants that keep the lights on. The takeaway? If it's big and made of metal, you can bet it was welded. Now, to get a handle on this huge field, it really helps to know that most welding techniques fall into two main categories. You can think of them as two different philosophies for creating that permanent bond. On one hand, you've got fusion welding. This is probably what you picture when you think of welding, using intense heat to literally melt the edges of two pieces of metal so they flow together and become one. But then, on the other hand, you have solid-state welding, which is kind of like magic. It actually joins materials without melting them, using incredible pressure and sometimes vibrations to force the atoms themselves to bond together. And wow, this slide really shows you how complex the family tree of welding is. I mean, look at all those different branches. We could honestly spend days just on this chart. But for our purposes, we're going to zero in on one of the most foundational techniques out there, one of the originals. So let's talk about oxyacetylene welding. This is a classic method, and it works by using the controlled combustion of two specific gases to create an incredibly hot flame, one that's perfect for melting steel. As you can see right here, the setup is actually pretty straightforward. You have a tank of pure oxygen and another tank of acetylene gas. Hoses connect these tanks to a handheld torch. Now inside that torch, the gases mix together and ignite, creating this precise, controllable flame that can get hotter than 3,200 degrees Celsius. That is seriously hot. The process itself is almost like a careful dance. First, the welder heats the edges of the metal pieces, and that creates a little puddle of molten metal that we call a weld pool. As the pools from both pieces merge into one, a filler rod, which is basically just a stick of compatible metal, is often melted into the pool to add more material and strength. And as the welder moves along the seam, the pool cools and solidifies right behind them, creating one single solid piece. This diagram is great because it gives us a really good close-up of the action. You can see the torch providing the heat, which creates that molten pool. At the same time, that filler rod is being fed right into the pool, and then, right behind it, the solidified, finished weld is formed. It's this continuous dynamic process that's happening in real time. But this is where the real artistry comes in. It's not just about applying heat. A truly skilled welder knows that the secret to a perfect weld is controlling the chemistry of the flame itself. Because that torch isn't just a simple blowtorch, it's a precision chemical instrument. By perfectly controlling the ratio of oxygen to acetylene, a welder can create three completely distinct flames, and each one has its own unique properties and purpose. First up is the neutral flame. This is your workhorse, your go-to flame. It has a perfect one-to-one mix of oxygen and acetylene. And it's called neutral because it doesn't really alter the weld metal chemically, which makes it perfect for most common jobs, like welding steel or aluminum. Next, what happens if you use more acetylene than oxygen? Well, you get a carburizing flame. You can actually spot this one because the excess acetylene creates an extra feather of flame. This flame adds carbon to the molten metal, which is really useful for welding high-carbon steels or for applying a hard, wear-resistant surface to something. And finally, if you crank up the oxygen, you get an oxidizing flame. This is the hottest of the three, with a shorter, more forceful flame that makes a really distinct roaring sound. You wouldn't want to use this on steel because it would literally burn it, but it's perfect for welding things like copper or brass alloys. This slide just brings it all together so well. You can see the visual differences in the shape of the flame, and notice that temperature range. The oxidizing flame is way hotter than the others. Even the sound is different. A skilled welder knows all these characteristics by heart, and they choose the right flame for the right metal. kind of like a painter chooses the right brush for the job.
So you've got the flame chemistry just right, but that's only half the battle. The physical skill of the welder, their hand movements, their technique, that is just as crucial to getting a good result.
A whole lot of factors go into making a high-quality weld, from prepping the metal edges to controlling how it might warp from the heat. But notice what's right there at the very top of the list? The skill of the welder. That human element is absolutely paramount.
A huge part of that skill comes down to technique, and in gas welding, there are two main approaches. What's fascinating is that the simple direction you choose to move the torch can completely change the outcome of the weld. So on the left, we have leftward or forehand welding. Here, the welder moves from right to left, essentially pushing the weld pool. The flame preheats the metal just ahead of the joint, which is fantastic for thin materials and gives a really neat finish. Then on the right, you have the total opposite, rightward or backhand technique. The welder moves from left to right, dragging the weld pool behind the torch. This concentrates the heat more, making it 20 to 25% faster, and it causes less distortion, which makes it ideal for thicker metals. It's a simple change in direction, but it leads to a totally different result.
So after all the chemistry, all the technique, and all this skill, here's what it all comes down to. The whole point is to create a joint that is just as strong as the original uncut pieces of metal. A weld shouldn't be a weak point. It should be a seamless, powerful continuation of the material itself. Welding really is this incredible blend of hard science and practiced manual skill, an art form that's as functional as it is foundational. So the next time you cross a bridge or see a building rising into the sky, take a closer look. You might just see the hidden art that's holding it all together. What do you think you'll see differently now?